Okay, good morning, everyone. As usual, how did your homework go? Put your question on the chat if you have any. Number 7, yep. Okay, any other questions besides number 7? Number 8 and number 6. Okay, so we're gonna do them by order. So I'm gonna start, oh, it's 11, so we can start. So we're gonna start by doing number 6. Okay, so we have the following. So we have the series f of x equal, we have the following function f of x equals 4 over 2x plus 3. And we want to write this as a power series in x. And the only thing we know so far is how to write two functions as power series. 1 over 1 minus x is 1 plus x squared, which is sigma x to the n equals 0 to infinity, and this one hold for absolute x less than 1. So we know this one. And another one, it's nice to know because it's very useful, is the one with a plus. And the one with a plus will be, if you remember, we rewrote it as 1 over 1 minus x, and we substituted minus x. The effect would be that this will be plus x squared minus x cubed, etc. It means instead of x to the n, I will have minus x to the n equals 0 to infinity. So those are the two major ones that everything we're going to do today will be somehow obtained by relating them to those two series. So now I go back to ours, the one which is sine, which is 4 over 2x plus 3. And now I need somehow to rewrite it. At this stage, I'm going to rewrite it to relate it to either one of them. It doesn't really matter which one. So you guys tell me how I'm going to manipulate this algebraically so I can relate to the first or to the second. Okay, you guys either in mute and tell me or write it up the best you can. That's the idea. I need to rewrite it to fit one of those and then do the substitution. So how can I do that? Okay, I'm listening, I am looking, everything. Divide by 3. Okay, so, or like factor out 3, right? Okay, I'm having, all right, so we're gonna do exactly what your classmates are saying. Since there is a 1 here, so I really don't want the 4. So I want, not the 4, I want really to factor out the 4. And I will be left with that. But this is also problematic because this work, it should be 1 plus x. That's what the geometric series tells me. So somehow we don't like this 3 right there. I'm going to factor it out as well. So I'm going to have 4 over 3. I'm factoring out the 3, 1 over. If I do that, I'm going to have a 1 plus 2 over 3x. So first step, related to one of those, either the minus or the plus. So now that's how I am relating it. So now let us see what I have. So now my x is, I write it bigger, so it's 4/3, that's my constant, 1 over 1 plus 2 over 3x. So that's my function, that's how I am relating it. Now I'm gonna go back and start substituting. So this is a plus, so it's easier to use this one. And so 1 over 1 plus x is 1 minus x plus x squared, etc. It means in plus x, so minus x cubed. Because sometimes I ask you only use the first 4 terms, so you should be able, we should write the first term and then we write in sigma notation. And this should be minus 1 x to the n, and this whole as long as x in absolute value is less than 1. That means if you take a value of x bigger than 1, you plug it here, this series will actually diverge. So this equality holds for those particular values of x. Now, based on this, I'm gonna take my function f. So my function f of x now is this constant for third that we can distribute times 1 over 1 plus 2 over 3x. So now this is gonna be equal to 4 over 3 times. And here I'm going to write it in sigma notation. All right. I'm going to substitute this term, this right here, this term, 2 over 3x, 4x in here. So I'm going to have 1 minus whatever that is x. I'm going to substitute it for 2 over 3x. That is x squared. I'm going to substitute it for 2 over 3x squared, and so on and so forth. So in sigma notation, I'm going to have the following. This is for third times. I should not forget the 4 third. And minus 1 to the n. And every time there is an x, I'm substituting 2 over 3x to the power n. Now, for which value of x this is valid? This is valid, this original one, it's valid when this x in absolute value less than 1. So this power series will be valid when the term I substituted for x, which is 2 over 3x, this is less than 1. So that's the setup. After that, we're going to do the algebra. It means I'm going to a little bit manipulate algebraically and have a nice expression for the power series of f. But that's the original setup. That's basically the most important setup. Now I'm going to do the algebra. So because we don't like that a lot, so now I'm going to move and do the algebra. I'm going to keep what I have in front of me and do the algebra. So this is going to be equal to 1. So my function f of x will be equal to, no, okay, the first with the terms and then in sigma notation. So let me focus on the terms first. So it's 4 over 3 times 1 minus 2 over 3x plus 2 over 3x squared. It means you multiply by itself twice. So this is going to give me 2 squared over 3 squared x squared. Now I know 2 squared over 3 squared is 4 over 9, but I want to keep it because usually we like pattern and etc. So that's in sigma, that's in writing up the terms. So in sigma notation is 4 over 3 times sigma minus 1 to the n equals 0 to infinity of. Now let's see, let me carry this. 2 over 3, the whole thing to the power n become 2 to the n over 3 to the n x to the n. And now for which value of x? So here I have 2/3 x in absolute value is less than 1. It means what are the values of x? Okay, let me do that. 2 over 3x, it means the 2 over 3 is a constant. I can pull it outside the absolute value. So this is going to give me, let us finish with that, x should be less than 3/2. It means the x I can put in here has to be less than 3/2. Otherwise, this series here will diverge. And now the last step is I'm going to distribute. Can you move the the paper up this way. Ah, okay. All right. Now I'm just going to distribute the 4/3 just so we do the algebra, and I can, because as long as you think of series as a sum, I'm just distributing a quantity multiplication. I'm just using the distributivity of multiplication with respect to addition. Okay, so now finally what my f of x is going to be equal to. It's 4/3 minus 4/3 times this. Now, if I do the math, 4 is 2 squared times 2. So it's going to give me 2 to the power 3. 3 times 3, 3 squared x. Plus, so I'm using the fact that 4/3 is 2 squared over 3, because it happened to be that simple. It doesn't have to be nicely. If I had a 5 in here, I couldn't have done this, but because I have a 4, that's easy. So finally, I will have plus 2 squared, so that's going to give me 2 squared over 3 squared times 2 squared over 3. So it's going to give me 2 to the 4 over 3 to the power 3 x squared plus etc. This is in terms. Now, if I distribute within the sum, and basically I'm multiplying term by term. So that's -1 to the n, and then if I take 2 squared over 3 and I multiply it by 2 to the n over 3 to the n, which is usually what I'm doing, I should have 2 to the power n plus 2 over 3 to the n plus 1 x to the n. My n should go from 0 to infinity. And this equality holds when the absolute x is less than 3/2. This condition guarantees the conversions of this series. And and the problem. Now let me check one thing back. I usually, when I write this, I like to ask myself, does this notation agree with this sum of terms? I mean, am I really at least compatible? So let me check. If n equal to 0, I have -1 to the 0, which is 1, 2 squared over 3, which is 4/3. I am fine. If n is 1, I'll have a minus in here, 2 to the power 3, 2 to the power 3 over 3 squared times x to the power 1. So at least my sigma notation and the sum of my terms agree on the first few terms. So I am basically a little bit on the right track. If n equals 2, that's positive. I'll have 2 to the 4, 3 to the 3, x squared, and so on and so forth. And that's the power series representation of the function f of x. Okay, so it's a lot of manipulation, but it's going to be, as you're going to realize in the next section and the section after, how important those manipulations are. So now I look at your other two problems, because we have to learn this stuff. So your other two problems were number 7 and number 8. So now I'm going to focus on number 7. And here is the problem. I have the function f of x equal x squared over x to the power 4 plus 16. Again, I need, so all of them happen to have the plus. You could have a minus. Again, I need to relate this to the series we know. And let's see which series we know. I'm going to relate it to this one, 1 over 1 plus x. So I'm going to rewrite it so I can relate it to what I know. So I give you a minute for all of you to rewrite it, a minute, and then we rewrite it together. So rewrite it yourself and see what happens. Okay, rewrite at least in front of you, and then I will do it for all of us. Remember, you have to relate it to what we know. That's really the bottom idea. That's what we know. And this. You have to relate them back to those. Okay, do it in front of you, please. Make sure you're doing it in front of you. Okay, who's ready? Who's ready? Okay, pull out the x squared. Okay, I'm going to pull out the x squared first. 1 over x4 plus 16. All right. And then I'm told to pull out the 16. So I'm going to pull out the 16. So this is going to give me, I'm going to flip those around. 1 plus x4 over 16. Do you agree with Sarah? Yep. And now can we just go on? I think we have it in the form 1 plus something. Now I have it in the format I want, and now I have to do the algebra. So that really should be our starting point. Relate to what we know. Relate to what we know. And so now let us see. So this is, I'm starting with 1 over 1 plus x because I have a plus and it's easier than using the minus. And those are easy to memorize. And this is sigma x to the n with a minus 1 to the n from 0 to infinity. And this one holds as long as an absolute value is less than 1. So now let us go to ours and start plugging in the numbers. So this is my f of x, and it's equal to, after rewriting it, it's x squared over 16, 1 plus x4 over 16. Okay, that's the rewriting. And now I'm going to do the substitution verbatim. So now I'm going to substitute this term right here. This is the term that I'm going to substitute for x. So this is going to give me equal to, and as I said, I will write the first few terms of the power series, and I will write it in sigma notation. So we basically become fairly flexible with the notation. So it's going to give me 1 minus, instead of the x, it's x to the 4 over 16. Instead of x squared is x to the 4 over 16 minus x to the 4 over 16 to the power 3 plus etc. Okay, and I always write it in both notation. I meant the first few terms and in sigma notation. So x squared over 16 times with the following. Sigma minus 1 to the n times the quantity x4 over 16 n equals 0 to infinity. That's the setup. Now, it's valid for which value of x? Because I'm substituting x4 over 16 for x, it means this should be less than 1. That's the condition on x. Isn't x4 over 16 at the beginning? I don't understand the question. That's x squared over 16. Okay, fine, thank you. All right, so now we're gonna just do the algebra and do the algebra basically. Sorry, I usually give you the, I need to scan those. So I won't, okay. I should remember that I usually scan this for you. So I forgot to number them. All right, so now let us do the algebra. So what is my f of x equal to? So my original function. Right. I'm going to multiply. No, before I multiply, I'm going to make those look a little bit nicer. And then I'm going to multiply. So x squared over 16 times 1 minus x to the power 4 over 60 plus. All right. If I take x4 over 16 and I square it, I'm going to get 16 squared down here. And x4 squared, we multiply the power. Multiply the power, which is going to give me x8. And minus 16 to the power 3. x4, 3, I multiply the power x12. Plus dot, dot, dot. And in sigma notation, this is going to give me x squared over 16 sigma plus c minus 1 to the n. My n start at 0 to infinity. And x4 over 16. It means 16 to the power n in here. x4 to the n, remember we multiply power. We multiply. It means 4 times n. And this is hold when this is satisfied. It means x4 over 16 less than 1. So let us finish with that. It means x to the power 4 less than 16. It means x less than the 4th root of 16, but this is equal to 2. So I got rid, I'm done with the domain. Now my last step is I'm going to distribute this term and finalize the answer. So I'm distributing, give me x squared over 16 minus. I'm distributing, so I might have to multiply x squared by x4. Since I am multiplying the same base x, different exponent, I'm going to add the exponent. So 2 plus 4, that's going to give me a 6 over 16 squared. Plus, so we're almost at the end, x squared times that, that's going to give me, we add powers now, over 16 to the power 3 plus so on. And in sigma notation, it's going to become n equal 0 to infinity of minus 1 to the n. And now I want to distribute this. It means basically what I am doing, and I'll explain here, basically what I am doing is the following. That's basically what I am doing. I am taking every term. Oops. What I am doing is the following. I'm taking every term, x to the power 4n, it's right there. Give me a minute, I put my act together. Every term is multiplied by x squared over 16. So basically I'm multiplying every term inside the sum by x squared over 16. So the general term is going to have 16n plus 1 in the denominator. And the numerator is going to be the 4n plus the 2. So that's really how we are multiplying. So now I put the answers here. X squared times x to the 4n. It means x to the 4n plus 2 over 16 times 16 to the n. Give me 16 to the n plus 1. So now I sum up. So this is my function. That's its power series. And it holds when the absolute x is less than 2. So if I take x equal 1, the equality will hold. If I take x equal 3/2, it holds, minus 1 hold. But anything that doesn't satisfy the condition absolute x less than 2 will cause this series to diverge. That's really what happened. This series will diverge. And if I take x equal to 3, the series will diverge. So the equality will be nonsensical. All right? So this takes care of number 7. Now I'm going to look at number 8. I may not finish it, but I will assign it for tomorrow because I think by now we had a lot of practice and you guys will do it. Okay, so number 8, it was the following. And f of x equal 2 x over 2x squared plus 1. So actually, never mind, this is not a hard one actually. But so we're gonna relate it to what we've done before, but they are making it easy for us because the 1 is being secured in this case. So I have 1 plus something. It's the x that gives me a problem, but we know that by now what to do with the x. We just basically factor it out. So let's do that. So rewriting this is not an issue now. This is x times 1 over, I'm just gonna 2x squared plus 1, I'm gonna rewrite it 1 plus 2x squared, so it will fit our picture a little bit more. And now this has become rather simple, and actually it's simpler than the one we've done before. So let us do it because it's not that hard. So this is my function, and my starting one, I always like to put the one that I'm going to relate to in front of me, so I will not lose track, etc. And when it is valid, always in front of me. So that's the summation of -1 to the n, x to the n from 0 to infinity. So this is, I just put it in front of me just so I can keep track. So now I go back to my function. So my function now is my f of x is x times 1 over 1 plus 2x squared. And now it's this 2x squared that I need to substitute for x. So this is going to give me x times. And this is x times the sum, and finally the domain. So let's do it step by step. All right, so we're going to have here 1 minus, instead of 2x squared, x is 2x squared, plus, instead of x, is that, minus, again, instead of x, plus, etc. In sigma notation, n start at 0, n goes to infinity, and it's -1 to the n. And instead of x, we have 2x squared to the n. The domain. This one works if this term in absolute value less than 1. So this one will work if this term in absolute value is less than 1. Now I'm going to make everything look nicer and I will be done. So let's make everything look better. All right, so it's going to be equal to, so my function f of x, it means x over 1 plus 2x squared is going to be equal to. First, I'm going to make those terms, simplify those terms, and then I distribute my x. So it's x times 1 minus 2x squared plus, believe me, when I test you on this, so many students take this term and don't develop it correctly. So 2x squared, let us remember, is basically 2 squared x squared squared. Now we're gonna keep it 2 squared, so this for the pattern, and x squared squared, you multiply the power, So it's gonna give me plus 2 squared, x squared squared is x4, minus 2 cubed, x squared to the power 2, we multiply the power, plus dot, dot, dot. There are a lot of terms. So in sigma notation, this is x times sigma, -1 to the n from 0 to infinity of 2x squared to the power n is 2 to the n, x squared raised to the power n is x to the power 2n. Now, what is the domain? 2x squared is less than 1, it means 2 times x to the power 2 is less than 1. So it means this is less than a half. It means x is less than the square root of 1/2. So these are the values of x that will be accepted. Now my final step is I'm going to distribute and finalize the problem. So finally my function f of x, it means x over 1 plus 2x squared could be written as follows. So it's going to be equal to x minus 2x cubed, x minus 2x cubed, plus 2 squared x5, x times x4, minus 2 to the power 3, x times x6, x7, etc. Equal, in sigma notation, n equals 0 to infinity of, okay, minus 1 to the n, 2 to the n, minus 1 to the n, 2 to the n. Now x to which power I have it. When I'm going to distribute this x, it means every x to the 2n, each one of them is going to be multiplied by x. So this is going to give me x to the power 2n plus 1. When is this valid? When the absolute value of x is less than a half. That's the solution to the problem. Now let me just make sure that the first few terms here agree with my sigma notation. I may goof. If n is 0, I minus 1 to the 0 is 1, 2 to the 0 is 1, x, that's work. N equal 1 minus 2, 2 plus 1, that's 3, it's working. N equal to 2, it's a plus, it's 2 squared, n equal to 2 times 2, that's 4 plus 1, 5, I am on the right track. And this is the power series representation. Okay, today we're gonna keep basically along the same line, but we're gonna find the power series of more functions. Basically, we wanna relate all of them to the one we know, but we need some kind of theorem to be able. So like what we're gonna do today, for example, is how can I write Ln as a polynomial of infinite degree, which is another way of expressing a power series. So we're gonna state a theorem that is gonna allow me basically to find a power series representation of this function. So it's going to allow me to write this function basically as polynomial. So this is the idea. I state the theorem, and then I will work with it. All right. So representation of function by power series continued. And there is the idea of differentiation and integration. In other words, suppose I have a function f. So these, you guys have the notes. You have a function f, and you can write it as a power series. You can write it as a polynomial of infinite degree. The question is, what about this antiderivative? If you take the integral of f, the antiderivative of f, which is a new function, what's its power series representation? And the idea is straightforward. Functions, if you write as a power series, we think of this always as a polynomial. So let's tell you that the antiderivative of f is basically the antiderivative of this polynomial, quote unquote. But how we find the antiderivative of the polynomial? So what's the integral of f of x dx? It's the integral of c0 plus the integral of c1x plus the integral of c2 plus the integral of that. So we can do term by term integration, which is sigma integral of every term. Of course, the theory is hard. The theory is not easy, but how to practice it is actually simple. So if I have a function and I know its power series representation, I know the power series of its antiderivative by taking the antiderivative of every single term. It means integral of f of x dx is the term-by-term integration of everything. And the theorem tells me that the power series of the antiderivative will have the same radius of convergence as the original one. It means if this one converges when absolute x less than r, term-by-term antiderivative will also converge for the same values of x. So, antiderivative of f of x dx, to find it, is antiderivative of this plus that plus this, etc. And actually the stretch, if a and b are two numbers which are within my domain, then the definite integral is the definite integral of C0 plus the definite integral plus the definite integral. So we can integrate term by term, whether indefinite or definite. So basically, I'm telling you, it means we treat power series like polynomials and we integrate term by term. That's really the idea. Okay, let's see how useful this is. So I'm going to practice that on the following function. So here's my function. Find a power series representation of f of x equal ln of 1 plus x. It means I want to write this function as a series. And the idea is we have to relate ln of 1 plus x to one of those. Now we cannot relate them the way we related them before. We're going to relate them differently. So how can we relate ln of 1 plus x to one of them? Now, of course, I'm giving you the solution here, but we should be able to know. What's the relationship between this one and that one? Take the integral. Absolutely. The derivative. Both of them are correct because both are telling me the same thing. The derivative of ln of 1 plus x, the derivative of that is 1 over 1 plus x. Find the derivative. It's 1 over the inside times the derivative of the inside, which is actually nothing more than 1. So the derivative of ln of 1 plus x is 1 over 1 plus x. Another way to write this is that ln of 1 plus x up to a constant is the antiderivative of 1 over 1 plus x. So that's my first step. I have to relate the function I want to something I know. And the relationship here is that the ln of 1 plus x is the antiderivative of 1 over 1 plus x. Now I know the power series of that. If we take term by term integration, I will know the power series of ln of 1 plus x. That's really how we're gonna do those problems. So I will, you guys have the notes, so I'm gonna rewrite them myself in front of you. And you don't have to write this stuff because it's already in your notes. But it's easier for me, actually, and it's simpler for you if I rewrite them here. So here I am. I'm gonna work out the problem. So we need ln of 1 plus x. My first step is to relate. So the relationship was that the ln of 1 plus x up to a constant, and I will talk about that, is basically the antiderivative. And now the way we're going to work is the following. I'm going to start with 1 over 1 plus x, the power series. Then I'm going to integrate term by term. And then I will get the ln of 1 plus x. So let's do that. 1 over 1 plus x is equal to. So step 1 is we relate. Step 2 is we integrate. It's 1 minus x plus x squared plus so on. And this is equal to the sigma. Now, ln, we know that is the antiderivative. So it's crucial first to see what we're going to be doing. So now I'm going to take the antiderivative of that. Why I'm taking it? Because that's what the ln is. Now, the theorem tells me that the antiderivative of this you can do term-by-term integration. The proof, as I said, those are hard proofs, but they are easy to apply. So let us do term-by-term integration. What's the antiderivative of 1? Now we're finding antiderivative of 1 is x. So term-by-term integration. Term-by-term integration. Minus. Antiderivative of x is x squared over 2. Plus. Antiderivative of x cubed over 3 minus x4 over 4 plus etc. So that's it. Now let's be a little bit more ambitious and let's see in sigma notation what's going to become. What's the antiderivative of x to the n in general? So now I'm doing the term-by-term integration. So it means I'm asking myself, what's the antiderivative of x to the n? But we know n is a constant power. So the antiderivative of that is going to be x to the n plus 1 over n plus 1. And n equals 0 to infinity. And it holds when absolute x is less than. We're almost at the end of the problem. Now, what's the antiderivative of 1 over 1 plus x? Because remember, my goal is the ln. That's really what I did, everything we did. So the antiderivative is the natural log. Now, of course, there is a substitution in order. I'm not ignoring that. So this is equal to that because if I take u equal 1 plus x, du will be my dx, and this will be 1 over u du, which is going to give me ln of u, which is going to give me ln of 1 plus x. So even though it's not x here, 1 plus x, but the small substitution will convince you that what I am saying here is absolutely correct. So now what's the antiderivative of that? It's ln of 1 plus x, and some student will tell me plus a constant. Okay, I'm going to put a constant in here, and I will take care of it in a second. So this is going to be equal to x minus x squared over 2 plus x cubed, etc. It means sigma n equals 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. So now what can I do? How can I get rid of the c? That's a little bit tricky here. The way we're going to get rid of the c is like that. So we're going to say plug x equal to 0 in both sides. And see if this will give me a c. If I plug x equal to 0, the first one will give me ln plus c equal. If I plug 0 here, I get 0. So this is going to give me 0 plus c equals 0 because ln of 1 is 0. It means my c is equal to 0. And with this in mind, I get the power series of ln of 1 plus x. So tell me that. ln of 1 plus x. It means if I take any value of x less than 1, then the ln of 1 plus x is actually going to be equal to, I'm going to copy this one, x minus x squared over 2 plus x cubed over 3 plus so on. It means it's equal to sigma from 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. And that's give me the power series representation of ln of 1 plus x. So, of course, you say, okay, it's too much. Why are we going to use this? How is this helpful for us? What this tells me basically is that ln of 1 plus x is a highly complicated function, regardless of what I tell you. But this tells me that ln of 1 plus x, we can intuitively view it as a polynomial of infinite degree. But eventually, the idea will be, which is we're going to talk about a little bit in the next section, that you don't have to take high degrees to approximate ln of 1 plus x. It means if I can start taking the first few terms, x minus x squared over 2, those will be enough to approximate ln of 1 plus x. So I can think of ln of 1 plus x as x. If I want better approximation, I can think of it as x minus x squared over 2. Better approximation, I can think of it as x minus x squared over 2 plus x3 over 3. So mentally, what I will be doing is I'm going to substitute ln of 1 plus x basically by those infinite polynomials and work with it. All right. So that's the power series representation of ln of 1 plus x. So let me now do something. It's not on your note, but it's like, no, this is you guys need. So suppose, just for the fun of it, suppose I take this power series. So this tells me that if I take any x, an absolute value less than 1, how did you find the range of x? The theorem tells you that when you take the antiderivative of the function, then the values of x, then the power series of the antiderivative holds for the same values of x that the original one holds for. It does not change. Meaning, if 1 over 1 minus x hold when absolute x less than 1, when you find the antiderivative, it will also hold for the same values as the original one. So if this one holds for x less than 1 absolute value, this series, this new series, also will converge for the same values of x. And that's really what the theorem tells me. So you can basically move the absolute value of x, okay? As I said, those are not trivial facts. The proofs are quite involved, but we accept them. So this tells me that if I can take absolute x less than 1, any x less than 1, and I plug it here for x, ln of 1 plus x will give me that. So I, just for the fun of it, I say, okay, let me take x equal minus a half. And I plug it in here. What does this tell me? It tells me that ln of 1 minus a half, which is ln of a half, is equal to this sum. Means if I take this, I plug minus a half in here, I should get that number. It means it should be equal to minus a half minus this square over 2 plus, let's see, minus a half cube over 3. I will write it in a second in a neater way. Minus a half to the power 4 over 4 plus etc. It means this should be equal to minus a half minus 1 over 2 squared times 2 minus, because I have minus to the power 3, 1 over 3 times 2 to the power 3 minus 1 over 4 times 2 to the 4. It means if I take this sum minus, I'm not going to write the sigma notation, 5 times 2 to the power 5. So this tells me that ln of 1/2, which is the same thing as minus ln of 2, is actually going to be given by this sum. If I add those terms, that's really what it's telling me. If I add those terms, I'm going to get plus etc. I'm going to get minus ln of 2. Now, if I might add them, it means ln of 2 is given by this sum. What does this mean to you? Means that we can start adding those terms. I should get ln of 2. So out of curiosity, and I start doing this. I start computing those terms. I was checking, will I get close to ln of 2? So of course I had, so that's S2. Then I started adding, physically adding. Because that's what this means. It means if I add those terms, I get closer and closer to ln of 2. And I pushed myself, I added S6, which is this one, the sum of the first 6 terms. And I added the first 10 terms, I physically added them, and I got those. I got those numbers. For S6, I got 0.69226. I didn't do S10, sorry. I did S8, I got 0.6927. I did S3, I got the 2/3, 0.66. Now, ln of 2 is what? ln of 2 is we pick up our calculator is 0.693. And that's exactly what's happening. When I was taking those partial sums, I was getting closer and closer and closer to 0.693. So this tells me that if I want to approximate ln of 2 and I don't have a calculator, it's really boiling down to add some sums, a little bit, and approximate the value of ln of 2. So this power series is giving me the tool to approximate ln of any number as long as the absolute x less than 1. It means I can approximate anything which is between basically 0 and 2. Because I want the absolute x is less than 1, it means the largest value x can take is 1 and the smallest is 0. So anything between, x between -1 and 1, it means 1 plus x, it's between 0 and 2. So I can approximate for those values, and I can find the value of ln of 1 plus x, which is very hard. Finding the value of ln is very hard. This is actually telling me you can find them by approximating it with this sum of numbers. Okay, so this takes care of ln of 1 plus x. Now I can play the same games and I can find, probably I'm going to give you as a homework for tomorrow, I can find the power series of arctangents. Okay, so I'll let you go after I ask you the following questions. Suppose I tell you find the power series of arctangent. Means I want arctangent as a polynomial. How can I relate it to what we know? And then we quit. Remember, I want to relate it to something like that. Or like that. Is it possible to relate the arctangent? Okay, again, somebody is telling me the derivative. So what's the derivative of arctangent? Is 1 over 1 plus x squared. Now I have it. It means that if I want to write this function as a polynomial, then I'm gonna need the antiderivative of that. And this would give me the arctangent. Now we know how to do this. That's easy. Now we take it and we integrate it term by term. And then I will be able to find the power series of the arctangent x. And that's going to be your homework for tomorrow. I actually want you to find the power series of arctangent x. And then I will assign problem where once you find arctangent x, I can give you arctangent of anything. I can give you arctangent of x squared. I can give you arctangent of 5x, which is I will. So once you find arctangent x, then you can write arctangent of anything in here, 5x, anything in here by substitution. Okay. All right. Any questions for any questions? All right, so please do your homework for tomorrow. I will look at your quiz and my and I will assign homework for tomorrow, which will be basically based on what I did today. So one of them will be you derive the arctangent x, and then you use it to do something else. Who is trying to? Adam, speak up. I don't understand. Adam? All right. Anyway, any question before I move on? Before we stop? All right, so please, your review is on Blackboard. Start working on them. I will review with you on Thursday, but start working on them so you have questions, very specific questions for me on Thursday. And if you have any questions about anything, join me in my office hours. All right? Okay, talk to you tomorrow. Bye-bye, guys.